All right, let's dive into a topic that sounds like it's straight out of science fiction, but is actually on its way to solving some of our planet's most massive problems: quantum genetic algorithms. So, I want you to imagine you're faced with a choice. But it's not just, A or B. It's a choice between trillions, maybe even quadrillions of options. And only one of them is the absolute perfect answer. How on earth would you even begin to find it? That right there is the heart of what we call optimization. And look, this isn't just some brain teaser. We're talking about really high-stakes questions. How do you design the most efficient power grid for an entire country? Or what's the perfect molecular structure to create a new life-saving drug? These are all optimization problems, and getting them right could literally change the world.
To really get a feel for this, let's look at a classic example, the traveling salesman problem. The goal seems simple enough. Find the shortest possible route that hits a bunch of cities and then returns home. But here's the catch. As you add more cities, the number of possible routes just explodes. It grows exponentially. This combinatorial explosion makes problems like this practically impossible for even our best supercomputers to solve just by brute force.
So if we can't just power through it, how do we tackle this insane level of complexity? Well, turns out we can take a page from nature's own 4 billion-year-old R&D department, evolution. Let's start with the classical idea, which is called a genetic algorithm. At its heart, it's this really beautiful and surprisingly simple concept. It's basically a computer program that mimics Darwinian evolution. Instead of animals, though, we have potential solutions to a problem, and we let survival of the fittest guide us toward the best one. So, here's the basic recipe. First, you get crossover, which is where two pretty good solutions, the parents, mix their information together to create new offspring. Then you have mutation, where you introduce little random changes. This is super important because it keeps things fresh and prevents the algorithm from getting stuck. And finally, fitness selection. All the solutions are tested, and only the best ones get to survive and become parents for the next generation. You just repeat this over and over, and the solutions evolve, getting better and better each time.
Now, that's already a really powerful idea, but what if we could give it a massive power-up? To do that, we've got to enter the truly strange, almost magical world of quantum computing.
On a normal computer, everything, and I mean everything, boils down to bits. They're like tiny light switches. They're either on or off, a 1 or a 0. Simple. But a quantum bit or a qubit, well, that's where things get wild. Because of a property called superposition, a qubit can be a 1, a 0, or, and this is the mind-bending part, both at the exact same time. This sphere is a fantastic way to picture that. A regular bit is stuck at one of two spots, the North Pole for 1 or the South Pole for 0. That's it. But a qubit? It can exist at any point on the entire surface of that sphere, representing this complex mix of both states. It just opens up a ridiculously huge space for doing calculations. And believe it or not, it gets even weirder. Quantum computers also use something called entanglement. This is where two qubits get linked together so deeply that their fates are intertwined no matter how far apart you pull them. If you measure one, you instantly know the state of the other. Einstein himself famously called it spooky action at a distance, and it's a huge part of what gives these machines their power. Okay, so we've got nature's clever evolutionary trick on one side, and the mind-bending power of quantum mechanics on the other. So, what happens when we smash them together? This is what you get: a quantum genetic algorithm, or QGA. This diagram from the research paper shows it perfectly. It's this beautiful fusion, right at the intersection of three incredibly powerful fields: the nature-inspired smarts of artificial life, the problem-solving muscle of optimization, and the sheer exponential power of quantum computing. So what does this actually look like? Well, in a QGA, that whole evolutionary process gets a massive quantum upgrade. Individual solutions aren't just strings of data anymore, they're represented by qubits. That means an entire population of potential answers can exist all at once in superposition. The crossover and mutation steps are now done using quantum gates. The big takeaway here is that you're exploring this huge, vast landscape of possible solutions all at the same time. Okay, this all sounds absolutely incredible, right? Maybe a little too incredible, which brings us to the really important question. Is this quantum way of doing things always better? Is it always faster?
The answer, and this might surprise you, is a bit more complicated than a simple yes. Quantum advantage isn't some magic wand you can wave at every single problem.
This chart from the research really lays out the trade-off perfectly. Okay, see the horizontal line at the bottom? That's speed, how much faster the quantum algorithm is. The vertical line is accuracy, or fidelity, basically how good the answer is. Being fast is great, but it's totally useless if your answer is wrong. The real win, the true quantum advantage, is in that top right corner, where you get both incredible speed and a high-quality, accurate solution. The authors of the paper put it perfectly right here. Speed up is great, but you can only rely on it if the answer is accurate. It really drives home the point that speed is only valuable when you can actually trust the result. The real goal is to build algorithms that hit that top right quadrant for the problems that matter most. So let's assume we can hit that sweet spot of speed and accuracy. What does the future look like then? What kind of revolution are we talking about?
Honestly, the possibilities are staggering. The research talks about using QGAs to design tiny, super efficient antennas for all our smart devices. They could optimize bus routes for an entire city in real time. They could create brand new molecules for medicine. They could even tackle huge problems in finance, logistics, or even something like improving plagiarism detection. The applications seriously touch almost every single industry you can think of.
And that leads us to the ultimate question. As this technology gets better and better, we're going to gain the ability to solve problems that we currently think are impossible. Problems that could lead to cures for diseases, create a truly sustainable global energy grid, or totally reshape our economy. So it really makes you wonder, when we finally have a tool this powerful, a key to unlock the impossible, what's the very first problem we should point it at?